most everything that a chemist does involves mixing things together in some way. So I thought now would be a good time to introduce some terminology and some ideas involved with mixtures. Mixtures. And in particular, I'll talk about homogenized or homogeneous mixtures. Homogenized implies that they were made homogeneous, but maybe they were homogeneous to begin with. So homogeneous mixtures. And you're probably asking, what does homogeneous mean? It means uniform or consistent throughout, that there's not a lot of variation in the mixture itself. And the most common word or the example of this is homogenized milk. Homogenized milk. I don't know if you've had the privilege of directly milking a cow or a goat, but you'll find very quickly that if you do, that the milk fat and I guess the non-milk fat separates very quickly. So if this is regular straight from the udder milk, you'll have a layer of fat that shows up there, and all of this stuff over here is much more liquidy. What homogenized milk does is it makes sure that all of this fat is dispersed completely evenly through the milk. So that's why when you go to your local grocery store and you buy homogenized milk, it's all nice and creamy throughout. And you don't get this, I guess some people actually like it, but you don't get this nice sheen of fat at the top, and just it all goes down a little bit smoother. So that's what homogenized means. So homogeneous mixture is the same thing, even and consistent throughout. Now, that is further divided depending on how large the particles that are diluted in the mixture are. So if we have a situation where the particles are larger than 500 nanometers, and that might sound large, but it still isn't that big, because a nanometer is 1/billionth of a meter. But if we have particles mixed in, say, water, but it doesn't have to be mixed in a fluid, or especially doesn't have to be water, that are greater than 500 nanometers, we're dealing with a suspension. A suspension. And the one characteristic that people associate with a suspension is that whatever you suspend in it, whatever you mix in, let's say I have a suspension here. Maybe it's water, just because that's easy for me to visualize. And I have some big particles here, that they'll stay in the water for some amount of time, but eventually they'll deposit on the bottom of the container. Or sometimes they'll actually float to the top, depending on whether they're heavier or depending on their buoyancy. They'll either float to the top or the bottom. And in order to get it back into the suspension state, you got to shake the bottle. So two examples I can think of this. One is mixed paint. Right? Before you paint your walls, you got to make sure that the can is well shaken. Otherwise, you're going to get an inconsistent coat. The other, I don't know, it's close to my heart, is chocolate milk. Chocolate milk. Chocolate. Chocolate milk. Chocolate milk. Because when you mix it up, it's nice and it seems homogeneous, right? It's nice, and I already have milk here. So at first when you stir it nice, you have all the little chocolate clumps in there, or at least the chocolate when I make it, it's like that. But then if you let it sit around for a long time, eventually all the chocolate is going to collect at the bottom of the glass. Right? Actually, different parts of it. I've seen situations where the sugar all collects at the bottom, and then you have these little clumps at the top. But you get the idea that the mixture separates. So these are and that's because the particles in either the paint or the chocolate milk are greater than 500 nanometers. Now, if we get to a range that's a little bit smaller than that, if we get to a situation where we're at 2 to 500 nanometers, we're dealing with a colloid. Colloid, and that word, I remember in 7th grade, I think it was, you learned it in science class, the colloid, and a friend and I, we used to, we thought it was a more appropriate word for some type of gastrointestinal problem. But it's not a gastrointestinal problem. It's a type of homogeneous mixture. And it's a homogeneous mixture where the particles are small enough that they stay suspended. So maybe, they could call it a better suspension or a permanent suspension. So here, the molecules are, so let's say that's my mixture. It's water. Maybe it's water. It doesn't have to be water. It could be air, whatever. Now the molecules are small enough that they stay suspended. So the forces, either their buoyancy or the force, actually more important, the forces between the particles and the intermolecular forces are kind of outweigh these particles' tendencies to want to exit the solution in either direction. And so common examples of these, I don't know, are well, the one I always think of when for me, this is the colloid is Jello. Well, Jello is the brand name, but it's gelatin is a colloid. The gelatin molecules stay suspended the gelatin powder stays suspended in the water that you add to it, and you can't you can leave it in the fridge forever, and it just won't ever deposit out of it. Other examples: fog. Fog, you have water molecules inside of an air mixture. And then you have smoke. Smoke. Fog and smoke. These are examples of aerosols. This is a aerosol in where you have a liquid in the air. This is an aerosol where you have a solid in the air. Smoke comes from little dark particles that are floating around in the air, and they'll never come out of the air. They're small enough that they'll always just float around with the air. Now, if you get below 2 nanometers, and I'm running, maybe I should eliminate my homogenized milk. If you get below 2 nanometers, I'm trying to draw in black. So if you're less than 2 nanometers, you're now in the realm of the solution. The solution. And although this is very interesting in the everyday world, a lot of things and this is a fun thing to think about in your house, or when you encounter things, is this a suspension? Well, first you should just think, is it homogeneous? And then think, is it a suspension? Is it eventually going to not be in the state it's in, and I'll have to shake it? Is it a colloid where it'll stay in this kind of nice thick state in the case of jello or fog or smoke, where it'll really just stay in the state that it's already in? Or is it a solution? And solution is probably the most important in chemistry. Although people talk about colloids and suspensions, 99% of everything we'll talk about in chemistry involves solutions. And in general, it's an aqueous solution when you stick something in water. So sometimes you'll see something like this. You'll see some compound X in a reaction, and right next to it they'll write this AQ. They mean that X is dissolved in water. It's a solute with water as the solvent. So actually, let me put that terminology here, just because I used it just now. So you have a solute. This is the thing usually is whatever you have a smaller amount of. So thing dissolved. And then you have the solvent. This is often water, or it's the thing that's in larger quantity, or you can think of it as the thing, the thing that's all around, or the thing that's doing the dissolving. Dissolving. For example, you could have sodium chloride in an aqueous solution. Or that means it's in water. And what's happening is the sodium and the chloride particles are dispersing. So sodium is positive, chloride is negative, an ion, because it took away the atom from the sodium. But when you put it in the presence of water, remember water, you have all the oxygen and the hydrogens. I've done this tons of times already. Oxygen and hydrogen. This is partially positive over here on this end. This is partially negative over here. So you'll have these larger, the positive sodium cation will separate from the chloride and be attracted to the oxygen ends of the water. And then the chloride, the negative anion, will be attracted to the hydrogen ends of the water. And that's what allows it to get dissolved, because these ions have some charge. They like to mix in with the water, which has these hydrogen, or has this polarity to it. And then let's see, the chlorine I'll draw here. It'll be over here with a minus charge. So this is probably the single most important thing to realize. And just so you get a sense of what 2 nanometers is, this is still pretty big. It allows for molecules that have anywhere from actually a good number of atoms. If you think of even a fairly large atom, cesium, the cesium atom, which is one of the largest, at least one of the largest that you might encounter, there are larger, is on the order of 2.6 angstroms. An angstrom is a tenth of a nanometer, so that's 0.026 nanometers. So for example, if you wanted a molecule that would get you out of the solution state and into the colloid, and we're talking in 3 dimensions here. So in 3 dimensions, you could actually fit a lot of cesium atoms within a 2 nanometer diameter sphere, although it's not like cesium doesn't bond in that way. But I think you get the idea that this is a scale of, on the order of 20 to 30 atoms can be in this molecule. Actually, even more than that, especially if you have very small atoms like hydrogen. So the next question is, well, how do you measure these things? And there's a lot of different ways to measure concentration. We already actually used one of them, which is mole fraction. Whoops. Mole fraction. Mole fraction. And this is the number of moles of solute divided by the number of moles in the whole solution, or moles of solute plus moles of solvent. And we did this when we figured out the partial pressure problems, because in order to figure out the partial pressure of something, you just figured out what the total pressure is, and then you said what is the mole fraction of, say, oxygen in the mixture, and then you multiply that times the partial pressure, and you got the mole fraction. Now the ones that show up a lot in chemistry, and since their words are so similar, it can get a little confusing, are molarity, not to be confused with morality. One day I'll make a video on that once I figure out enough about it. And molality. And molarity, it sounds like the right one because it's almost like morality, and it has the word molar in it, which it's more, for me, more intuitive than the word molol. But molarity in my mind is not a good measure because it's moles of solvent, moles of solute, so what you're dissolving into it, divided by liters of solution. And the reason why I don't like molarity much, and you'll see that molality is actually, at least in my opinion, more useful, but the reason why I don't like this is because liters of solution is not invariant. It changes, right? We've learned that a bunch. PV equals nRT. The volume, which liters is a measure of, volume can vary with pressure and temperature. So the molarity is going to vary with pressure and temperature for the same solution. If you just take the same solution and take it, to Denver or take it to Death Valley, the molarity of the solution is going to change. So to me, that isn't that satisfying of a measure of concentration. Molality, on the other hand, is moles of solute. So the numerator in both cases is essentially the number of solute particles we have. The number of particles we have divided by the mass of the solvent, or the kilograms of whatever we're being dissolved into. And the reason why this one is better is because no matter where you go, whether you're in Denver or Death Valley, moles aren't going to change. They didn't change here either. And the mass won't change. Now the pressure and the volume and all of them, the temperature might change, but the mass won't change unless you're adding more or less solvent. So this, in my mind, is kind of the better one. And actually, I'll put a little contest on this video if y'all can think of good ways to remember the difference between molality and molarity, because frankly I think this is one of the most, it's not confusing, they're very simple definitions, but I think a lot of people get confused, especially a year or two out of taking chemistry class. If someone says, oh, what's the difference between molality and molarity, you're like, oh, well, there was a difference with volume and mass, but I forget which is which. And I'll leave it up to you guys to think of a good way to memorize the difference between the two. See you in the next video.